Claude Fable 5 is the model people are already using every day, but every one of them is renting it because nobody has ever had a copy of their own. And if you wanted to try, the biggest unified memory you can buy in a single machine today tops out at 128 gigabytes in an M5 Max MacBook Pro. That ceiling actually went down this year when Apple pulled their 512 gigabyte Mac Studio. And against Fable's estimated 14.5 trillion parameters, 128 gigabytes isn't close. So what would it actually take to run Fable 5 locally? Anthropic sells access to Claude Fable 5 through their apps, cloud partners, and the API. But every one of those surfaces just sells you access to a model running on somebody else's hardware. So if you look at their official launch page, they are very happy to charge you per million input tokens, but nobody is handing over the actual model or a spec sheet. And because they have never actually published the model's architecture or parameter count, if we want to build a physical cluster to hold it, we first have to figure out what number we are even building against. The only working figure we have is an independent estimate circulating right now that guesses Fable sits at roughly 14.5 trillion total parameters, shaped as a mixture of experts model. But that number rests on a chain of inference, because it relies on a second-hand quote from DeepSeek's founder and assumes Anthropic is using the exact same sparsity ratios as DeepSeek V3. The estimate's own author admits that if Anthropic used a less aggressive ratio, the real weight could drop closer to 10 trillion parameters. Every single link in that chain is a place the math could break, which means our purchase order is basically aiming at a speculative range. So we are forced to provision enough server racks, physical GPUs, and networking cables to catch a worst-case 14.5 trillion parameter behemoth, fully aware we might just be overbuilding. To figure out exactly how much physical memory a model of that size actually occupies, you just pull up the standard LLM hardware requirements math. The industry rule of thumb is that you need about 2 gigabytes of memory for every 1 billion parameters. So if that 14.5 trillion parameter estimate is anywhere close to reality, running it at full FP16 precision means you're looking at roughly 29 terabytes of memory just to hold the weights. Obviously, nobody actually does that, which is why quantization exists, to shrink the footprint by crushing the model into lower precision numbers. Dropping down to INT8 gets you to roughly 1 gigabyte per billion, meaning we still need about 14.5 terabytes of space. And if you compress it all the way down to 4-bit, the published math comes out to roughly 0.6 gigabytes per billion. That brings the physical footprint down to roughly 8.7 terabytes of VRAM. But that is the absolute floor, where you stop saving money and start paying for that space with actual reasoning quality. And the beautiful part is that it doesn't even matter if our initial estimate is wrong, because if we run that same 4-bit math on the conservative 10 trillion parameter guess, you still end up needing about 6 terabytes of memory sitting in one machine. For scale, just loading a much smaller 405 billion parameter open model at full precision demands around 810 gigabytes of VRAM. That alone is already beyond any Homelab machine in existence, let alone something trillions of parameters large. So our single line item for memory just became 3, and the absolute cheapest option still asks for multiple terabytes in a single pool, which means the purchase order is dead in the water before we even look at a physical graphics card. So to actually hold those terabytes, you have to look at the physical hardware you can buy and plug into a motherboard today. The absolute best consumer graphics card on the market is the RTX 5090, giving you exactly 32 gigabytes of GDDR7 memory. And at a retail price of $1,999, taking that 8.7 terabyte floor and dividing it up means you're looking at buying about 272 of those cards just to hold the weights, which makes the standard desktop look a little pathetic. If you try to fall back on the biggest single machine you can buy, that route is worse than it used to be, because at 128 gigabytes per M5 Max MacBook Pro, holding the 4-bit requirement takes about 68 machines. And a Mac Studio is no help either, because Apple's current one stops at 96 gigabytes. Which means the consumer approach is completely dead. forcing this order into the data center, where an H200 holds 141 gigabytes, bringing your total down to about 62 GPUs, or roughly 8 full server nodes. And even if you manage to grab the newer 192 gigabyte Blackwell parts, that pile only shrinks to about 46 GPUs. The uncomfortable thing here is that none of this hardware is exotic or theoretical, because every single component has a known price and a real lead time, turning an abstract memory footprint into a very literal, very expensive pile of metal you have to acquire. So, a pile of consumer graphics cards seems like it solves the capacity problem, but the catch is that a frontier model doesn't actually run in a couple hundred separate boxes. For the weights to be useful for inference, the model has to treat all of that VRAM as one continuous memory pool. And consumer hardware from NVIDIA is built to work alone, meaning those boards physically lack the interconnects required to share memory across a cluster. That's assuming you could even find a standard motherboard with enough physical slots to hang them all off of, without starting a small electrical fire in your garage. When a model is split across unconnected cards, every time it processes a layer that lands on the wrong GPU, your memory problem turns into a traffic problem. This is what the enterprise hardware is actually charging you for, because the premium on data center parts is for the proprietary wiring that lets all that memory talk to each other fast enough to matter. Which means a new class of constraint appears that no spec sheet advertises, because the connection between the parts is suddenly more important than the parts. You can't just buy the cheapest units and bolt them together. The cheap route does not get more expensive here. It stops existing. The moment you group 8 server nodes together, your build stops being a computer and officially becomes a full server rack. And a server rack is strictly not furniture, meaning you can't just shove it under your desk or hide it in a spare bedroom, because it demands the kind of electrical draw that would instantly melt your breaker box. It needs industrial cooling that a residential house absolutely does not have. And it has to sit on a poured concrete floor designed specifically to hold the weight of all that screaming metal. The funny thing is, even the companies buying up these data center parts mostly don't actually own the physical rooms they live in either. They lease the floor space, the chilled water lines, and the power delivery from the big cloud providers. Which means the moment your hardware order gets big enough to require its own dedicated room, you lose the ability to actually host it yourself. The order crosses the line from buying a computer into commissioning a facility, which puts you right back to renting space from the exact same corporate giants you were trying to escape, just one layer down. So if you ignore the physical room entirely and just ring up the 272 consumer graphics cards we stacked up earlier, you're looking at a bill of about $544,000. Assuming you can actually find them for their $1,999 MSRP. And remember, that $500,000 pile is the version of the machine that does not work, because the server nodes that actually have the wiring to run it use data center hardware that costs more per unit. Which means we need to look at the other side of the ledger, where Anthropic is selling access to Claude Fable 5 for $10 per million input tokens and $50 per million output tokens.
And if you keep your context warm, they throw in prompt caching that cuts the cost of repeat requests. So the actual bill for a working application drops even further. But the really painful part for the hardware owners is that even renting the physical metal itself just got cheaper. Because as the new Blackwell supply started landing, the rental market for H200 nodes saw a complete collapse, dropping around 40% in just 3 weeks. Basically, every single price in this entire comparison moved aggressively in favor of renting, and absolutely none of them moved in favor of trying to squeeze a data center into your spare bedroom. In a mixture of experts model, not all of that memory actually has to be doing something at once. The defining trick of this architecture is routing, which means instead of firing every single parameter for every single token, the model sends each piece of work to a small, specialized subset of its experts, while the rest stay quiet. DeepSeek V3 is the public reference for this shape, lighting up just 37 billion active parameters per token out of its 671 billion total.
And if you apply that same ratio to the public estimate of Fable 5, you get a model running roughly 800 billion active parameters per token. At 4-bit quantization, that active footprint demands about 480 gigabytes of unified memory. That is still about 4 times the biggest machine you can buy. And to a determined person with a lot of reckless optimism, it's a handful of boxes rather than a data center rack. But the inactive experts still have to physically exist in the machine somewhere, and the system has to fetch the exact right parts for the next token before it can actually generate anything. So the requisition order changes, because your bottleneck moves from how much VRAM capacity you can afford to how fast you can rip data through the physical cables connecting it. If you think this whole memory juggling act is just some white paper theory reserved for the big cloud providers, it turns out that real people are already running models exactly like this tonight. The developers behind llama.cpp recently added options that make offloading inactive experts to ordinary system memory totally trivial, and the local AI community picked them up immediately. The pattern is basically a digital shell game, where you park the pile of inactive parameters in your computer's standard RAM, which is cheap and plentiful, so you only have to keep the active experts loaded directly on your expensive graphics card. When the router needs a specific piece of the model for the next token, it just yanks it across the motherboard right when it needs it. This is exactly how home builders are stretching consumer hardware onto open architectures that have no business fitting on their physical cards. And you're skipping the custom orchestrator entirely, because the routing flags are literally just one line in a command you run from your terminal. The whole process runs so reliably that it's already crossed from being a brittle research project into just a standard Tuesday for local enthusiasts. Every single piece of this technique is completely free and available to anyone right now, but it comes with one hard condition attached, because you can only run a model this way if its creators actually published the weights. The catch with parking most of a model in ordinary system RAM is that the physical wiring connecting your motherboard to your graphics card is a miserable, narrow bottleneck, and every single token generated has to pay that toll. So if offloading makes it fit, why isn't everyone doing this for everything? The answer is that pushing this much traffic across consumer hardware introduces a completely different failure mode, where your machine prints out the exactly correct answer at a pace so agonizingly slow, you'll wish it had crashed. Because dragging heavy chunks of inactive weights back and forth across a PCIe slot for every single word is roughly like trying to drain a swimming pool through a cocktail straw. If you're just typing into a chat interface, you might actually tolerate watching the text arrive one word at a time at a pace you can comfortably read along with. But the moment you put that same model inside an agent loop that needs to make dozens of invisible background calls to parse files and review a codebase, that slow trickle compounds into a system that is unusable. So an honest definition of running a model locally has to include a usable speed alongside the mathematical fit. Getting a terabyte-sized pile of parameters to physically sit inside your hardware and buying a machine fast enough to actually talk to them turn out to be two entirely different purchases. The natural instinct right now is to just wait a few generations for consumer hardware to catch up, because that's exactly what happened to the first wave of models. We watched those early architectures that used to demand a dedicated server rack slowly shrink down into things you could comfortably run on a normal desktop card. But total parameter counts are climbing way faster than the physical memory you can buy, and even the open models are following the frontier's shape rather than the consumer's budget. You'd normally expect the consumer ceiling to climb every year, but this year it actually went backwards. Apple used to sell a Mac Studio with 512 gigabytes of unified memory, and in March 2026, they pulled that configuration entirely. The cause of that drop is the AI build-out itself, because memory manufacturers reallocated their production toward the high bandwidth memory stacked inside AI accelerators, making ordinary DRAM scarce. So they pulled the 256 gigabyte option too, and the machine now stops at a hard ceiling of 96 gigabytes. Which means the exact same demand that makes frontier models bigger is literally taking the memory out of the machine you'd use to escape them. And the irony here is that the sparsity trick making the models cheap enough to serve suggests they probably won't ever fit in your house. Because a mixture of experts architecture only wakes up a fraction of its parameters for each token. The big AI labs realized they can keep inflating the total size of the model to make it smarter without actually inflating their cloud bill. Sparsity makes adding billions of dormant parameters incredibly cheap for the companies renting out access. So the total size of the pile you've got to download is only going to accelerate. So the gap between the hardware you can physically purchase and the models they're building isn't closing, because it's actively being stretched from both ends. The actual ceiling for what a person can run on one buyable machine today is whatever fits in 128 gigabytes, which by that same per billion rule is a bit over 200 billion parameters at 4-bit. That means the 120 billion class open mixture of experts releases fit comfortably, with room left for context. The really big open models, like DeepSeek V3 and the largest Qwen models, are still reachable, but only by offloading to system RAM or spreading across a multi-GPU workstation. That local ceiling is still an enormous amount of capability sitting in your house, but it's 1 to 2 orders of magnitude below the frontier estimate. And that gap makes sense when you look at what the closed scale is actually being hired to do. Forbes reported 80.3% on SWE Bench Pro, and Stripe reportedly used it to migrate a 50 million line codebase in a single day. So instead of asking if your local graphics cards can match that enterprise fever dream, you just have to decide which of your actual daily workflows need that last stretch of accuracy. When you have to rewrite an entire legacy architecture overnight, you swallow the API cost and rent the server room. But for standard engineering loops and the local debugging that makes up the bulk of your week, the biggest model you can cram under your desk is already smart enough to do the job. So let's say you actually clear the physical hurdles, rent the facility, and wire up a literal rack of data center cards to run this thing. The hardware was just the easy half of the problem, because when you go to pull Claude Fable 5 down to your new server node, you'll realize the final line on your multi-million-dollar purchase order cannot be filled at any price. Anthropic sells a service billed by the million input tokens, not the weights themselves, which means there is no secret enterprise tier and no backdoor price tag that gets you the actual model. And if you think a blank check solves everything, the even more capable sibling model is completely withheld from public release and shared only with a small set of approved partners, even as the Forbes headline announces, Anthropic launches Mythos. The most expensive item on your requisition form costs absolutely nothing, because it represents a business decision somebody else already made. You didn't hit a physics constraint or a budget limit, you hit an access wall. And the whole fantasy of how to run it locally dies right here, because there are no weights for anybody. So the final requisition asks for terabytes of pooled memory, dozens of data center GPUs, and a reinforced room to plug them into. The physical hardware is brutally expensive, but entirely ordinary, meaning you could technically build this facility if you hated money enough. But the line item that kills the project is the free one, because Anthropic keeps those weights strictly behind an API, and there is no tier you can buy that includes them. Which means this entire build sheet is basically a procurement dead end, and the hardware worth buying is for the models you were allowed to download the whole time. The biggest open mixture of experts releases are completely yours to keep, and if you quantize them properly, they will comfortably slide right into the 128 gigabytes you can actually buy. That machine fits on a desk, the weights run locally tonight, and you get to let some cloud provider pay to build the data center for the frontier stuff. Anyways, that's all folks.